Hello and welcome to this session in which we will be studying a new data type called graphs. Graphs are a natural generalization of sequences and trees that we have studied so far. So, if you have seen in a sequence, every node or element in the sequence has at most one next node and at most one previous node. So, the first node does not have a previous node, the last element does not have a next element. Otherwise, every element has one previous element and one next element. In a tree, every node has at most one previous node, which we call the parent, except the root node, which does not have any parent. But a node can have any number of next nodes. They are called children in a tree. So, a node can have any number of children, but it will have at most one parent. So, a graph is obtained by just relaxing all these conditions. In a graph, a node can have any number of previous or next nodes. So, what is a graph? So, it consists of a finite set V of nodes, also called vertices, and a collection E of ordered pairs of nodes. So, an ordered pair n comma m is in the set E, then it is said to be an edge from the node n to the node m. So, E is a collection of edges which are essentially ordered pairs of nodes n m. And if Nm is an edge, then we say node m is adjacent to node m or a successor of node m. So, node m is like a next node of n, but n can have any number of successors and they are defined by the set of edges in the graph G. Similarly, node n is said to be the predecessor of node m or the previous node of m. So, again m can have any number of nodes as previous nodes or predecessors, and which nodes are predecessors or successors is defined by the set E of edges in the graph. So, the set V defines what are the nodes in the graph, and the set E defines the ordered pairs, which defines which nodes are successors of which nodes. The out degree of a node is the number of its successors and the in degree is the number of its predecessors. So, let us look at some examples of graphs. So, a graph of say air connections. So, here the nodes are the cities in the country and there is an edge from node n to node m if say there is a direct flight from city n to city m. So, the airline can represent their flights by a graph depending on which cities the flight connects. So, there may be an edge from node n to node m if there is a plane flying from node city n to city m. So, if you look at courses offered in an institute, there is a graph which defines their structure and an edge indicates, so the nodes are the courses, set of all courses, and edge nm indicates that course n is a prerequisite for course m. So, you can do course m only after completing course m, and this relation between courses is indicated by the set of edges in the graph. Similarly, if you look at a graph of student registration, now here nodes can be of two types, they are students as well as courses in the institute, and an edge nm indicates that student n has registered for course m. So, the registration data in an institute can also be represented as a graph where the nodes are students as well as courses. So, we will look at how a graph is represented. So, a graph is just defined by a sequence of nodes in the graph and a function called successor nm that returns true if and only if node m is a successor of node n in the graph. So, we have a sequence of nodes which represents what are the nodes in the graph and a single function successor that tells us whether a given node m is a successor of node n or not. So, this is also called the adjacency matrix representation of a graph, because for every pair of nodes it tells us whether a given node m is a successor of node n or not. Any functions on graphs can be defined using just these two things. We need to know what are the nodes in the graph and we need to know which nodes are successors of which nodes. If this is defined, any operation on graphs can be defined using this. Alternatively, sometimes we can define a graph using in a different way by defining a different function called successors of n that returns a sequence of successors of node n. So, rather than giving a pair of nodes and telling us whether m is a successor of n, this gives us the list of all successors of a given node n. So, you give a node n in the graph, it will tell you what are all its successors in the graph, and this is sometimes called adjacency list representation. Both representations are equivalent. A graph can be represented in either way, and we will choose whichever representation is more convenient depending on its use. So, there are some standard terms used in a graph which we will define here. A walk in a graph. So, walk is essentially motivated by some of the examples that we have seen. So, if for example, we have a graph of direct flights from city I to where an edge represents a flight from city I to city j, and we want to go from some city x to some city y. Now, there may not be a direct flight from x to y, but then how do you go from x to y? So, for problems like this, we define these terms like walk and, as we will say, paths and cycles. So, what is a walk? It is just a sequence of nodes, and it is defined as the following. The empty sequence is not considered to be a walk in a graph. A walk containing a single node or a sequence of nodes containing a single node is a walk. So, walk of push n comma phi is true, and walk of push n comma push m comma s will be true only if m is a successor of n and walk of push m comma s is true. So, that is, if I take a sequence that has first element n and second element m, then this sequence is a walk if m, the second element or second node, is a successor of the first node, and the remaining sequence obtained by removing the first node is also a walk. So, essentially a walk is a sequence of nodes where every node in the sequence is followed by one of its successors. A path is a similar thing. So, it is a sequence of nodes defined in a very similar way. It is false for the empty sequence. For a sequence containing a single node n, it is true. Now, here we have the extra condition. So, apart from the condition in a walk that m is a successor of n, that is, the second element must be a successor of the first element, the remaining sequence must be a path itself, and we have this extra condition that occurs n comma remaining sequence must be false. That is, the first node in the sequence must not occur anywhere else in the sequence, and this should hold for the remaining sequence also. So, essentially this says that is a path is a sequence of distinct nodes. We do not come to the same node again in the sequence. So, path is a sequence of distinct nodes which is a walk, also a walk. So, the occurs function essentially tells us whether a given node occurs in a given sequence of nodes. So, occurs n comma phi is false, occurs n comma push m comma s is true if n equals n, otherwise it is true if n occurs in S itself. This will be useful later also. And similarly, another very useful concept in a graph is that of a cycle. So, it is again a sequence of nodes defined similarly. If it is empty, it is not a cycle. On the other hand, if it is non-empty, it must be a path. So, the sequence must satisfy all the properties of a path, and the additional condition that the last element of the sequence or the first element of the sequence must be a successor of the last element of the sequence. So, last of push n comma s comma n successor should be true, which just says that the first element of the sequence n must be a successor of the last element of the sequence. So, last here is a function that returns the last element in a sequence. It is undefined for the empty sequence, and it can be defined in a usual way for any non-empty sequence. So, here are some exercises. So, assume you are given the representation of a graph as a sequence of nodes and a function successor nm, which tells us whether m is a successor of n or not. Using this, we can write a function successors m that returns the sequence of all successors of a node n, and we can also do the converse. Given a function that returns all successors of node n, we can write a function which tells us whether a given node m is a successor of n or not. And now we can use this to write a function called predecessors n that returns the sequence of nodes that are predecessors of a given node n. Or similarly, we can write a function predecessor nm which tells us whether m is a predecessor of n or not. All functions on graphs can be defined using just these two. So, understanding these will be crucial for understanding graphs. Thank you.